Hello students, today we discuss numerical problems. So in this discussion, here there is a problem in your exercise of oscillations. A simple pendulum of length 100 centimeter performs S.H.M. So from this sentence we get one value that length of simple pendulum is 100 centimeter. In SI system it can be expressed in meter. It is 1 meter. The question is, find the restoring force acting on its bob of mass 50 grams. Bob of mass 50 grams. M is equal to 50 grams. We write it in SI unit, 50 into 10 raised to minus 3 kilograms. In the sentence there is question, find the restoring force. Means we have to calculate F. And again one value is given when the displacement from mean position is 3 centimeter. Means X is given, X is equal to 3 centimeter. It can be 3 into 10 raised to minus 2 meter. So from these values we have to calculate F. For F, restoring force is given by F is equal to minus Kx, or it is minus M omega square X. By magnitude, F can be written as magnitude. F is equal to M omega square X. So we must have to know M is given. Omega is not given, but length is given. From length we can calculate omega. X is given. So we have to find out first the omega. The first step in the problem is we have to find the omega. So for omega we take T is equal to twice pi under root L upon G. T is equal to twice pi under root L is equal to 1 and G is equal to 9.8. So we write here T square is equal to 4 pi square 1 upon 9.8. So that we can write for omega square, because we know omega is equal to, here omega is equal to twice pi upon T. Therefore omega square is equal to 4 pi square upon T square. So once we know omega square, we can substitute in this equation. F is equal to M omega square X. So the next step of the problem is F is equal to, it is not the second question, the same question is there, but steps are different. Here this is first step, this one is second. F is equal to M omega square X. M into omega square into X. So F is equal to M into omega square is 4 pi square upon T square. 4 pi square upon T square into X. F is equal to M into 4 pi square. T square we have expression, this expression we have for T square. We can substitute it 4 pi square upon 9.8 multiplied by X. X can be substituted here. We can substitute here M also. F is equal to, M is 50 grams, is 50 into 10 raised to minus 3. It can be written as 5 into 10 raised to minus 2. 15 into 10 raised to minus 3, we substitute as 5 into 10 raised to minus 2. And x is 3 into 10 raised to minus 2. So f, that is restoring force. Here what can we simplify here? 4 pi square gets cancelled. 5 into 3 is 15. 9.8 denominator of denominator, it can be shifted in numerator, multiplied by 10 raised to minus 4. Now this multiplication, it is equal to into 10 raised to minus 4. It is expressed in Newton. 147.0 into 10 raised to minus 4 Newton. So this is the answer. Restoring force we have to calculate in this way. So it is a simple problem. We have to write for S, but omega is indirectly given. In terms of T, we can calculate it, and then substitution gives us the restoring force. Now the next problem is the period of oscillation of a body of mass m1 suspended from a light spring is T. The situation is like this. There is a spring, is light spring, to which a mass is suspended. That mass is m1, and if it is oscillated about its mean position, say O, then time period is found to be equal to T. Period of oscillation is T. So for m1 mass, period is T. Now the next sentence, when a body of mass m2 is tied to the first body and the system is made to oscillate. How can we show the system here? Is again the same situation. Here the first mass is m1, and again to the first mass, second mass is attached, it is m2. The system is made to oscillate. The system is made to oscillate means m1 and m2 both. This system is made to oscillate here about say mean position O, and time period is found in this case for m1 plus m2. System is having mass m1 plus m2 and time period found is twice T. Compare masses m1 and m2. We have to find the comparison or ratio of m1 and m2. This is the question. If the data is in this way. So for the first situation, we write the equation for period as T is equal to twice pi under root m1 upon k, because the formula for period is T is equal to twice pi under root m upon k. But in our case, m1 is replaced by m1. K is the spring constant and period is T. So letter T is used in the problem, therefore we have used it as T. So this is equation number 1. For the second situation, we write the formula for period. Here T period, but here in this case the period is twice T. We substitute in the formulation. Twice T is equal to twice pi under root. Instead of M1, we take the mass of system, which is M1 plus M2, and it is divided by K. Spring is same in both the cases, therefore spring constant is also same. Masses are different and periods are different. We have taken into consideration that point. Now if we divide equation 1 by equation 2, or say 2 by equation 1, we can get here the next step is dividing equation 2 by equation 1. We get is twice T divided by T is equal to twice pi we get cancelled, K also we get cancelled, and inside the square root there is M1 plus M2 divided by M1. Because if we divide equation 2 by equation 1, twice pi is constant, in both the cases K is constant, it cancels. Now this equation can be simplified in the next step. Here T would also get cancelled, we get here 2 upon 1 is equal to under root M1 plus M2 upon M1. Squaring on both sides. Squaring on both sides. 4 upon 1 is equal to M1 plus M2 upon M1. So 4M1 is equal to M1 plus M2. Therefore, thrice M1 is equal to M2. M1 upon M2 is equal to 1 upon 3. This is the comparison or ratio between two masses M1 and M2. You have to understand this simplification. It is also very simple. In the first situation, we have taken a single mass M1 and its period is T. Equation is written. In the second situation, for the second sentence, this description, when a body of mass M2 is tied to the first body, means M1 and M2 are tied, and again the system is oscillated, we get the period as twice T. Therefore, equation 2 we have written by using the formula, and then simple adjustments are there. Dividing equation 2 by equation 1, we get 2 upon 1 is equal to M1 plus M2 upon M1, and simplification gives us M1 upon M2 is equal to 1 by 3. Now let us solve this problem. A wooden block of mass M is kept on a piston. So first we mean the piston. So motion of piston is the best example of oscillatory motion. Here in the engines, pumps and some mechanical instruments, this piston is used. It is simple arrangement that there is a cylinder. In that cylinder there is a piston. So this is a piston, and usually it is a metallic piston. This piston moves up and down. So here, if the original position is denoted by M, upper extremity by M, lower extremity by N. This motion is up and down. So as there is up and down motion, it possesses some energy due to vibratory motion, and that energy is supplied to other parts of the engine. So this is one of the most important parts in the engine. Now on such piston, there is a wooden block of mass M. So here there is a block and its mass is M. Now during vibration, we don't want the block to leave the contact with the piston. So there is vibratory motion. Even if the piston moves to upper extremity or lower extremity, it does not leave contact. This is the condition. We don't want block to leave contact with the piston. So here the force is adjusted in such a way that here weight of block is adjusted with the force which is restoring force. That is, mg is balanced by the restoring force. So here the x can be taken as a. So even if it moves to upper extremity or lower extremity, then its restoring force must be balanced by the weight of block. So here we take the example, we take the relation here. Weight must be balanced. Here weight must be equal to restoring force at the upper extremity and lower extremity. So once we know the relation, we can calculate the values which we have asked here. How much maximum frequency is possible if amplitude of vibration is restricted to 25. So here omega can be calculated and then frequency or period can be calculated. Also there is one more question. In this case, how much is the energy per unit mass of the block? So first we calculate the omega and then proceed. So here mg we consider mg is equal to m omega square a. Mm will get cancelled. G is equal to omega square we write as 4 pi square n square, and a is there. So here n square can be equal to g upon 4 pi square a. It is given that g is equal to 10 meter per second square and pi square is given equal to g. So both these values we can use. Any one value we can use here. So I can here take the calculation on this side. N square is equal to g, that can be substituted by 10. 4 into pi square can be substituted as 10, and a is 25 into 10 raised to minus 2 in meter. So 10 will get cancelled. Here we get 4 into 24 is 100. 100 into 10 is to minus 2. So we get here n square is equal to 1. Therefore n is equal to 1 Hz or 1 oscillation per second or 1 vibration per second. This is the frequency. How much maximum frequency is possible if the amplitude of vibration is restricted to 25 cm. So this is the first answer. Now read the next one. In this case, how much is the energy per unit mass of the block? Energy is given by, here energy is equal to half m omega square a square. So especially kinetic energy or potential energy is not asked, simply energy is asked, therefore we take it as half into k into a square, half into m omega square into a square. And energy per unit mass is asked, therefore we take m in denominator of LHS. E upon m means energy per unit mass is equal to half into omega square. Omega square is 4 pi square and square. So try to remember for the omega. Omega always we have to take into calculation. Omega is equal to 12 pi n or 12 pi upon t. So easily in omega square you can put this 4 pi square n square or 4 pi square upon t square. So here please. Now we can calculate it. So calculation is simple. Half into 4 into pi square given approximately 10. N square is 1 square. A square is 25 into 10 raised to minus 2 square. So we get here 2 into 10 into 1 into 625 into 10 raised to minus 4. So what can we get here? 625 into 2 is into 10 raised to minus 3. 10 into 10 raised to minus 4 can be adjusted like this. So this is the energy per unit mass and it is joule per kilogram, because the quantity is not simple energy, it is energy per unit mass. So here we write answer energy per unit mass, which is asked. It is 1250 into 10 raised to minus 3, or it can be 1.25 joule per kilogram. So this is the problem solution. Let us solve this problem. In this, a 20 centimeter wide thin uniform disc of mass 200 grams is suspended to a rigid support from a thin metallic spring. This example we have studied in theory for angular oscillations. So there is a thin spring, this is spring, and this one is disc. You know it is the support. This support. Now this disc is 20 centimeter wide, means its diameter is 20 centimeter. So that its radius is 10 centimeter. It can be written as 10 into 10 raised to minus 2 meter. Here the unit is meter. And M, mass of the disc is 200 grams, means 200 into 10 raised to minus 3 kilograms. It can be written as 2 into 10 raised to minus 1 kilogram. By holding the rim of disc, the disc is twisted through 60 degrees. Means here it is just like our rotation. For any body, we rotate the body in this way. We twist it and then rotate. Similarly here, disc is twisted. Here the twist is given and that twist is through 60 degrees. So theta is equal to 60 degrees. And release. It now performs angular oscillations of period 1 second. T For the time of oscillation it is 1 second. So when the disc is twisted and released, then it performs angular oscillation, and for in this situation t is equal to 1. Calculate maximum restoring torque generated in the string. Here torque we have to calculate. Torque is equal to minus c theta. Torque is equal to c theta if only we consider the magnitude. So first we have to calculate this c. C means restoring torque per unit angular displacement. So if we know c, then we can calculate the maximum restoring torque. Because theta is known, is 60 degree or it is pi by 3 radian. So we calculate for c. It can be P is equal to twice pi upon, general equation it is twice pi upon angular acceleration per unit angular displacement. T is equal to twice pi upon under root, angular acceleration is alpha, displacement is theta. So twice pi alpha upon theta. But alpha upon theta can be calculated like this. Suppose this is first equation. So we know it is I alpha is equation 2. So we can equate I alpha is equal to C theta. RHS can be equated. So we get here alpha upon theta is equal to C upon I. It can be substituted here. T is equal to twice pi under root C upon I. Therefore we get T is equal to twice pi under root I upon C. Here squaring on both sides we get T square is equal to 4 pi square under root I, squaring the square root we get I upon C. But T is given, it is equal to 1. Therefore we take 4 pi square I upon T square and substitute for T square. So once we know the situation, here we can write on this side. C is equal to 4 pi square I upon T square. T square can be substituted as 1. 1 second. So we have relation for C. So we can write from equation 1. From equation 1, tau is equal to C theta. Here C can be 4 pi square I divided by 1 into theta is pi by 3. 4 pi cube into upon 3 into 1 it is 3 multiplied by I. Here I is not directly given, but the quantities M and R are given here, and here we have for disk moment of inertia. We have studied in rotational dynamics. For the disk it is mr square by 2, which is the moment of inertia about the axis which is perpendicular to the plane of this disk. So let us substitute it here. 4 pi cube upon 3 into mr square by 2. So once we have the relation for tau, after substitution we can get the maximum value. So let us substitute here. 4 into pi cube is given in the problem. It is 31. Is divided by 3. M we have adjusted it as 2 into 10 raised to minus 1. Now also R can be adjusted as 10 into 10 raised to minus 2. It can be adjusted as 10 raised to minus 1 and square. It is divided by 2. Simplification gives us 2 will get cancelled. Here 4 into 31 divided by 3 is 0, 3, 3 multiplied by 10 raised to minus 3. 10 raised to minus 1. 10 raised to minus 1 square is 10 minus 2. We get like this. And multiplication gives us 10 raised to minus 3 Newton meter. It is the unit of torque. It is the maximum torque. It is the maximum torque when the oscillations are with the angle pi by 3 radians. So here 4 into 31. So here we have to write here 10.33. Sorry for that. Is 41.32 into 10 raised to minus 3 Newton meter is the answer. So this is there are some problems I have given in the notes, and you have to refer those problems. Also you have to solve the numerical problems which are given and solved in the book. So that is the homework for you. Thank you.